And it is along this spread version that I will measure the spreading of the probability measure. So this is the idea. So here is the definition. Okay, I will do it in several steps. So let x d nu be a geodesic metric space with the measure nu. Okay, nu, a nice finite Borel measure, and let's say it is compact. Otherwise, you need a bit more definitions. Okay, so define W2 as follows. If I have a measure mu0 and a measure mu1, it will be the square root of the optimal transport to go from mu0 to mu1, which will be defined as follows. The infimum of the integral distance x0, x1 square, pi of dx0, dx1, where the infimum is taken over all measures pi, which belong to capital pi of mu0, mu1, that is, which have marginals mu0 and mu1. In other words, such that the double integral of phi of x plus psi of y, pi of dx dy, is equal to integral phi d mu0 plus integral psi d mu1. So this has an interpretation, and it is what I was explaining in the public lecture. Like, you have a given configuration of initial mass, and you want to rearrange it into the final mass, which is given also, and each time you move 1 unit of mass from this place to that place, you pay a cost which is the square distance. And you want to minimize the total cost that you spend. Okay. Why the square? I would say, you know, here it's a Riemannian context, the square is very natural. Square distance appear everywhere. In fact, this problem is general, you can set it for any cost, and depending on the context, it could be a certain cost or another cost. For some applications in physics, it could be this or that. Square distance appears in most applications in physics or geometry. In physics, because it has a taste of kinetic energy, you know. So this is the optimal transport cost. And when you take the square root, W2 is a distance, is a real distance on probability measures on X. It's even a geodesic distance. So actually, the space of probability measures equipped with W2 now is a geodesic space. And now comes the second definition. So this optimal transport problem has a long history in statistics. It appears with the first occurrence is with Gaspard Monge in the 18th century, in which case the cost function was just the distance. Then it reappears in the work of Kantorovich in the 1940s, and from there it is developed by various authors, in particular with statistics applications. It has many different names depending on which power you put of the distance. By far the most important cases are the two which I gave here, or the other one which you take, you put just the distance and not the square root. Next definition, if nu is given, then h nu of mu, if mu is a probability measure, will be the integral of rho log rho d nu, where rho is d mu over d nu, and plus infinity if mu is not absolutely continuous with respect to mu. This is the usual Kullback information or for Shannon information or Boltzmann information, which measures the spreading of mu with respect to nu in a way which is meaningful in a number of fields. Okay. And now here is the definition. X d nu is CD of 0 infinity if for any mu 0 and mu 1 in P of X there is a geodesic. So it's a path mu t for a t going from 0 to 1 in P of X equipped with W2 such that for any t in 0, 1 h nu of mu t is bounded above by 1 minus t h nu of mu 0 plus t h nu of mu 1. Okay, so that's the definition. And what is the idea behind this definition? It's a way really to say for intermediate points, when you move from one measure to the other, how much it is spread. And one can show that for a smooth space, this is equivalent to the usual definition. So this really is a generalization. But then this is more general and stable, as you would expect from a synthetic definition. And also it implies some inequalities which are typical of CD 0 infinity of the classical one. So this was the basis and the simplest, and the question is whether this can be turned now into a whole theory in which there are all the theorems that you would like to be. When these programs started around 2005, there was a number of problems on the list of what should be proven so that it is acceptable, and it took about 10 years to solve all these obstacles. A number of people contributed until we can see that now this is quite satisfactory. So let me tell you about some of the obstacles and some of the various generalizations that needed. So generalizations, extensions. So first, here I gave you the simplest case, which is CD 0 infinity. Now you will tell me, you will ask, what about CD of Kn? General K, general N. Well, it took quite some time to find relevant ways. There are several ways to do it. I will give you just one which works. It's the one in the literature which is called CDE of Kn. And it's very simple. It's almost the same as this, except for the very last part. You see here, this is the linear interpolation of h nu of mu 0, h nu of mu 1, and time t. Well, it turns out to give the CD of Kn, we will just replace this by something else. Okay. So what is this something else? Replace L of ABT by the following function, by psi of AB, and here it will be K W2 square of mu 0 mu 1 t, which is the solution function means a function with second derivative is equal to 0. Instead of second derivative equal to 0, you will say second derivative, I will write this with dots, psi double dots, minus psi dot square divided by, okay, let's use a simpler notation, just like this. And here I will put the n, and here this will be equal to k w2 mu0 mu1 square. Okay? So it's a function which is time it's nonlinear. It depends on k and on n, and the solution you use it to define to give your definition. Now I have a small hesitation whether it is n or n minus 1. Let me just check here. No, it's okay. Yes, it's okay. Okay. So, and then this gives you a criterion which then this is consistent with the usual CD, with the smooth CD of Kn. It is stable, and it is stable. Okay. Next problem.
So does this equation, it just comes from by a back calculation, or that also has some geometrical or
It comes from it's analytical. It doesn't
so
have any. Yes.
Back calculation.
It doesn't have a really geometric interpretation. Not that is obvious, you know. Just one comment. It makes sense because this thing satisfies the maximum principle. You see, because when you want to look at the maximum, this thing vanishes, so you are left with the second derivative. Otherwise, it would make no sense to do a comparison, you know. If I try to make a definition with, for instance, the third derivative, it would not work. It took quite some time to find this simple thing, and most of the credit for this goes to Sturm. Next, here was another thing. Another thing is the compatibility with CAT. You know, Ricci curvature is the sum of sectional curvatures. So if I impose some assumption on the sectional curvatures, it will imply something on the Ricci. For instance, positive or non-negative sectional implies non-negative Ricci. Okay. And these things are fair. This should also be the case at the synthetic level. So an assumption on CAT should imply an assumption on the Ricci. But the CAT is expressed in terms of triangles and the Ricci in terms of entropy. So you have to find a connection. And this is a problem about geometry of CAT spaces, of Alexandrov spaces. And it was solved by Petrunin. And so, for instance, any space which satisfies CAT plus 0 and dimension bounded above by n, in the Hausdorff sense, for instance, will also be CD0n. So there is a compatibility, and it's not absolute. The next thing was the compatibility with the class. I will call this classical non-smooth analysis in metric measure spaces. So there is a whole general theory of analysis in metric spaces, which was in particular developed by the Nordic schools. And also by Chigger, who can be considered as a school in himself. And in this setting, well, it's based on Sobolev spaces and how they are defined, and there is a mantra that always you should first start by checking doubling inequality, Poincare inequality. Every paper in this school starts by let X be a space satisfying Poincare inequality and doubling inequality. And so, also again, it should be compatible. So to prove that the CD spaces imply the doubling is easy. This is the content of the basically the Bishop-Gromov inequality, and it turns out it can be adapted rather easy. So we did this long ago to prove that CD implies the Poincaré inequality is not so easy, and was done by Hayala with all the generality that one can hope for. So the answer is yes. As soon as you have the CDKN, you also have the Poincaré doubling, and there is compatibility with all these theories. Now, one thing you also would like is the Laplace operator, because Ricci is very often associated with the estimates about the Laplace and so on. And here there is a beautiful result by Ambrosio Gini Savare that says yes. Savare. Whenever there is CDKN, for any k any n, for some k, some n, then there is a heat semigroup. This heat semigroup is canonically defined as the gradient flow, as the W2 gradient flow of H nu, or equivalently as the L2 gradient flow of the Dirichlet form. And so there's a unique heat semigroup. That semigroup sometimes is linear, sometimes is not. And this will lead us to the next problem. So far so good, and so far we have an extreme generality. For when the theory was out, however, some geometers were dissatisfied and says this is too general to be applicable, and in particular, they were very much irritated by the following example. So, problem, take Rn and put any norm you want. And then take the Lebesgue measure. Satisfy, with this, it will satisfy CD0. So, you will say, why not? This is a very nice and a very bad space, depending on how you look at it. It's not a Cartan-Alexandrov-Toponogov space, the norm is not Euclidean. And it's a space that never arises as a limit of manifold. And for geometers, for some geometers also, the greatest sin is that it does not satisfy the so-called splitting theorem. So splitting is one of the most important results in constructing tangent spaces in non-smooth situations. And splitting theorem is the following. There are a number of versions of this, and now there are even some generalization for higher dimensions in some sense with some kind of scalar curvature. Anyway, splitting theorem says the following. If you have a manifold M with Ricci non-negative, and gamma is an infinite minimizing geodesic on M, in M, then you can split M as a product of gamma by, well, this gamma will be an R across something. And that something also will have Ricci non-negative. So if you have the infinite line, you can factorize the geometry by this infinite line if the Ricci is non-negative. Now, this is a theorem that is true for Riemannian manifolds, but it is not true for this space. Obviously, if you take an Rn which is not Euclidean, in general, it will not be the product of R by some Rn minus 1. So, to continue, it was important to have somehow a restriction that if you want, you can apply to restrict to cases like this. And the solution was found by Gili. Define a subclass of geometries. Let's call it RCD, so R will be for Riemannian. And which are the following. They satisfy the CDKN, and so here is the one possibility. The Sobolev space W12 of X is a Hilbert space. And this last property is equivalent to saying that the heat equation is linear. So some geometry satisfies this, others not. And as a major result, Jelly shows that RCD satisfies the splitting theorem. So it's a non-smooth version of this splitting theorem. Here is a comment. This condition says that when you look at integral grad f square, it should be Hilbert, so this should be defined a quadratic form. And obviously, it's a, since grad f is morally a tangent vector field for any f, this is a way to say that the geometry is kind of Riemannian, but in a way that is spread. It looks very natural. Yes?
You mean an upper gradient?
Okay.
For non-smooth spaces?
So. This will be the, it's the minimal L2 norm of the any upper gradient. Something, yes.
Any upper gradient.
Absolutely. You take among all upper gradient, you take one which has minimum L2 norm. Yes. So let's put with a minus or something. Has to be with little care. It's a construction that was studied in great detail by Chigger in the old days. So why did people not do it before? One main reason is that if you look just this condition alone, it is not stable by Gromov-Hausdorff, by measure Gromov-Hausdorff. But if you look at the combination of two, it becomes stable. The analogy, and this is very nice, is with the fact that if you try to define, if you take a function, you can always define a gradient in weak sense, in approximate sense, or whatever. But it will not be stable under pointwise convergence. But if you have a lower bound on the second derivative, like convexity, then it will be stable. If you have a sequence of convex functions, then the gradient will converge to the gradient. And so this is the analogy. This is like a second order bound, and this is like a first order pointwise condition. And the combination of the two is stable. So this is, yes?
So is this RCD, KN compact in NG?
And then the RCD are compact.
It's compact.
Absolutely. Not pre-compact, compact.
So
CD are compact and RCD is compact also.
So does this mean, if you use if you rescale the metric, divide by a large, multiply by a large constant.
Yes.
So you get weak tangents exist?
In some, yes. There are some theorems like this, absolutely. And only with somehow...
maybe not uniqueness of the weak tangent.
Yeah, not uniqueness, but also for the moment, people are unable to prove that the dimension of these tangent spaces is the same all over the space. But it's a problem that seems within reach. And this splitting theorem is indeed a tool that you use in this construction. The experts in this now are Mondino and Naber. They use this to show that if you take an RCD space, then automatically it is rectifiable. Automatically rectifiable. So there is a tangent space defined almost everywhere. To be really satisfactory, the only thing that is needed is to show that the dimension is bounded by this capital N and that it is independent, almost surely, of the point that you are interested in. But yes, it is rectifiable. So here we are almost there. So this was an important step, and then it's okay. It's as you want. Sometimes it's very good to be able to consider these spaces. For instance, they have the same, this Rn space has the same isoperimetric profile as the usual Euclidean space in some sense. So it's good to have a unified theory. But if you want to study the local properties, it's good to have the splitting theorem, so it's better to stick with RCD. So the RCD are a subclass which you can study on your own, and the closure of Riemannian manifolds under MGH is included in RCD, which for the moment is the smallest that we can define synthetically that contains the manifold. And let's finish by saying that finally, with these approximately all of the good inequalities that one was interested in have been shown to be true. So finally, within RCD, Kn, one can prove. So I already told about Poincaré and so on, but also spectral inequalities, concentration inequalities, how you call Liao heat, kernel inequalities, Bochner inequalities, and isoperimetric inequalities. So, and even sharp sharp L2 Sobolev inequalities, etc. So, all the classical inequalities which appear in the theory, you can reprove in a non-smooth way within this category, and in some cases even get the equality cases. So, in this sense, the theory satisfies all the basic requirements up to some refinements like the one I was discussing. Let me say that the recent one, which stood open for quite some time, and that was for me the most important, was finally proven by Cavalletti Mondino in 2015. And it is the so-called Levy-Gromov inequality. I will conclude with this, and it will also give an answer to one of the questions, which is, why do you want to do all this? And there are several motivations, but people doing non-smooth analysis, some of their motivation is, I want to find the good proof which should be good even in the smooth case. And for this, I remove the smoothness assumption and I try to do it without. So the most important isoperimetric inequality in non-Euclidean context is the so-called Levy-Gromov. And it's a comparison inequality. And it says the following. Suppose I have a manifold like this, which satisfies CDKN with K finite, positive, and finite. And I have a set A in this manifold. And then I want to compare somehow the volume of A and the measure of the boundary of A. Isoperimetric problem. Now here is an auxiliary space, and this is a sphere of dimension n. And the radius, that will be, gosh, I always mistaken, probably it's square root of n minus 1 divided by k, right? Okay. The one for which there is inequality. And now here you take a comparison, and this will be a ball, B. Here this is a solution of the isoperimetric problem. And in such a way that the volume of A divided by the volume of M should be equal to the volume of B divided by the volume of S, the sphere. And M is this manifold. M is the manifold, A is the part. So I take another thing which has the same relative ratio as this, as a comparison. Then the measure of A, of the boundary of A, is bounded above by the measure of the boundary of B. It's a neat inequality, beautiful comparison principle, which captures also very well the meaning of Ricci curvature. Now, when you look at the proof of this, it's a very delicate proof, in requiring a lot of smoothness on M, because at some point the theory of minimal currents is used, the geometric measure theory from the 60s, and you go through the rectifiability. You need, I don't know, 8 derivatives or something like this for the classical theory. And the proof is monster. You need to prove that minimizing shape is rectifiable, and this is no joke. It's just the big works of Almgren and these other people. And when you see this, you think there should be a softer proof, which does not use the smoothness. And this is what Cavaletti-Mondino proved indeed, using this theory of synthetic Ricci curvature, and a new trick, beautiful trick, which is called localization, which also has a history going back to the theory of convex geometry, and that I will not talk about. But anyhow, they find the right way to give a proof which applies to any of these RCD-Kn spaces, or even to so-called non-branching CDKN, when you are sure that geodesics cannot bifurcate. So in a way, it's an inequality which can even go outside of the non-smooth Riemannian case. And so with this, no smoothness is needed, no recourse to the theory of geometric measure theory, minimizing currents or whatever. And this was, I think, for anybody who cares about the regularity and about how long should an analytic geometric proof would be, and what it should involve or not, this is an important achievement. So with all this, I will conclude it here. Mention that some of the directions in which, other directions in which the theory has been pushed are Finsler geometries, for which you can also adapt, discrete geometries by perturbing a little bit, and the connection to Alexandrov spaces can be refined in some sense. So let's say that now it had stood the test of time, and that 10 years after the program was started, we can say that it really fits. And with this, I thank you for your attention.
Well, ladies and gentlemen, all things must come to an end. We had a fantastic lecture from Professor Villani. Any questions?
The Wasserstein space, you said it's a geodesic space. Is that true even if the underlying metric space is not geodesic?
No. In fact, there is equivalence. This one is a geodesic space if and only this one is one.
So in the definition using optical construct for CDK, you need the underlying space to be geodesic.
Yes. Yes. Actually, I will. There is properties that are strong. First, so there is a space below. Let's say this is X, and above there is P of X. So the relation between X and P of X is very strong, and actually, when you think about it, X embeds isometrically into P of X, and the isometry is just for each X you associate the Dirac mass. And then there is also the topology is inherited, and convergence here is equivalent to convergence there. The spaces X converge in the Gromov-Hausdorff topology if and only if P of X converges in the Gromov-Hausdorff topology. So it is an equivalence. That one is metric space, is a geodetic space. Also, that is an equivalence is a CAT actually. That one is a CAT space if and only if that one is a CAT space. With a CAT 0 if and only this is CAT 0. It doesn't work for the other values than 0, but for CAT 0 it works.
So is there any hope of defining CDKN if the space has no rectifiable paths, for example? So say for example, boundaries of groups, hyperbolic groups, typically have no rectifiable paths.
Yes, but this rather belongs to the negative curvature world, no?
Yeah, but the boundaries, there's a hope. Maybe if you take the classical HN, the boundary is SN. So,
I see.
Yeah. But the problem is the metrics look like snowflake metrics. So you don't have rectifiable paths.
One would have to massage
Yeah.
things quite a bit, you know. I don't exclude it. I don't exclude it, but one would have to.
But you said it makes sense for discrete spaces.
Yes, yes, yes.
How do you?
By introducing an error, let's say, because you know when it's discrete space, one is, let's say, there is a typical length scale, you know, let's say it's epsilon, and then you define Ricci at scale epsilon, you know. In the context of CAT, this was also done, you know, these approximates Alexandrov spaces, and here do something like this. Typically, what is of interest, at least to me, to a number of people, is we take spaces depending on the parameter n, and in such a way that it converges to some limit space, and you want to know the asymptotics as n goes to infinity. And then it would be okay because, you know, for instance, you can define approximate geodesic and geodesic at the scale epsilon. So you put this in the inequalities and it will work. So some of the people who have looked at this in particular are Olivier, Maas, there are some others, Paulin, and then you can do it either through the distance or through an operator if it is more Markov chain complex and you want to take the operator. But for instance, one of the results of Olivier was that, which is kind of emblematic, if you take this space with a uniform measure, then the correct is Ricci bounded below by 1 over n. And this is the optimal. So that's the kind of result that you can show. That the n goes to infinity, there is lower bound, like 1 over n. And there is some combinatorial interpretation and so on, but it's really a discrete geometric setting.
Yeah, so you mentioned this Olivier paper, which was today, one digging.
Really?
Some of us. No, so but struck to me that somehow this Olivier paper, I saw that this, so they have also a quantitative analytic definition of curvature.
Yes.
Wrote something like a paper or something. So do you think is that possible in your approach, or this some of the space? Not the synthetic one, but from the analytic one, some kind of.
It is no. The Olivier paper is okay. What he says is, let's look at as W1 between let's say PT mu 0, PT mu 1, where this is a bit of the heat equation, and compare this with W1 of mu 0, mu 1. Okay. He does it with W1, you could also do it with W2 in some sense. In RCD, the two approaches are equivalent. But when you are discrete, it's not equivalent. You have to choose whether you prefer the heat or the distance. What Ambrosio-Gilli-Savare shows is that in RCD, heat is canonically associated with the distance and everything is equivalent. Now, when it's not RCD, you have to choose.
So I mean, does that mean something like this? I mean, I may be wrong, but then that in each CDK and you just wrote that you can have associated to it a Dirichlet form and each semi-group.
Yes.
So in some sense, so you have an associated Markov process which you can call a Brownian motion in code, and you look at its exit time asymptotics.
Yes.
So
In RCD, you can define a Brownian motion.
The two coincide.
Yes, absolutely. Absolutely. Yes, yes. And it's compatible with the classical theory of non-smooth Dirichlet forms and so on. Yes.
Any other questions? Comments? Right. Thank you, Professor Villani.
Thank you.